Hey grades, here we go. Section 11.3, last section of the year. What? So last section, we were looking at how we can find total number of outcomes just by multiplying the outcomes from each event. We're going to be doing sort of the same thing, but actually now instead of determining just outcomes, determining probabilities using multiplication of fractions. So let's look at some examples. So we're gonna make our table. So okay, we have the spinner. Mackenzie spins the spinner divided into 5 equal regions. Also rolls a 4-sided die. She does each of these once. So A asks us to construct a table to represent the sample space and then see how many possible outcomes there are. Okay, so let's do that. So with the spinner, I'm going to put the spinner on top. Remember, it doesn't really matter which place you put each one. The spinner has purple, green, red, blue, and yellow. It's nice that those all start with a different letter. Okay, purple, green, red, blue, yellow. And then the die I'll put along the side. It has 4 numbers. 1, 2, 3, 4. Okay, I can erase those ends. Sort of make it a bit neater. There we go. And now I can fill it in. So you could roll a 1 and spin purple, roll a 1, spin green, roll a 1, spin red, roll a 1, spin blue, roll a 1, spin yellow, 2 in purple, 2 in green, and so on. So you just spend the time filling this out. 2 yellow, 3 purple, 3 green. Yeah, 4 purple, 4 green. Sorry. Just slowly doing this, almost done. Well, I can't talk and do it. Okay, there we go. Have it filled in. So how many possible outcomes are there? We can count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. It's 20, or like we learned last time, if there's 5 possible outcomes here, multiplied by the 4 possible outcomes here, we're going to have 20 possible outcomes. Okay, so there we go. We know there's 20 possible outcomes. So B, from the table, what is the probability of blue and a 2 expressed as a fraction? So let's use a specific color. So for B, red, I'll put a dot beside that favorable probability. So blue and 2, B and 2. There's only one of those, blue and 2. And so we said there was 20 favorable or 20 total outcomes. And so blue and 2 would be 1 outcome out of the 20 total outcomes. So now we can also use multiplication to determine the probability of blue, comma 2. And so this is how we do it. We look at each event. So if we wanted to find, for C, probability of blue, comma 2, that's the same as the probability of blue, just that event, multiplied by the probability of getting a 2 in that event. So if we just look at the spinner, what is the probability of getting blue? Well, it's 1 out of 5 is the probability. Well, what about the probability of getting a 2 on the 4-sided dice? Well, it is, probability of 2 is there's 1 2 out of the 4 outcomes. And we can multiply these fractions together. Now you have to remember a bit about multiplying fractions, but you just multiply the top and multiply the bottom. 1 times 1 is 1, 5 times 4 is 20, and so we get 1 out of 20, which when we looked at our table and found that one event is the same answer. So we can take our probabilities from each event, for each of the events that we're looking at, and we can multiply them together to find the probability of both of those things happening. Okay? So there's how we can find C. We can multiply instead. Okay, so what about B? I'll use green here. From the table, what is the probability of red or blue, so either one of those is favorable, if it's with a number less than 4? So this symbol is less than. So red with a number less than 4, so red and 1, red and 2, red and 3 are all favorable. Or blue with a number less than 4, so blue 1, blue and 2, blue and 3, those are also all favorable. But anything with green or yellow or purple isn't favorable, and nothing with the number 4, just less than it. So those 6. So we can see as our fraction, when we use our table, it is 6 out of the 20. There's 6 favorable outcomes out of 20 for probability of red or blue and a number less than 4. Okay, well, what about if we did E here using the method from part C, so using multiplication of fractions? Can we find probability of red or blue and less than 4? Well, we take those two things. What's the probability of getting red or blue from our spinner? Well, red and blue is 2 outcomes out of the 5 outcomes would be favorable. And a number less than 4 on our die would mean numbers 1, 2, and 3, which would be 3 outcomes out of the 4 outcomes. Okay, 2 over 5 times by 3 over 4. We just multiply the top numbers together, multiply the bottom numbers together. 2 times 3 is 6. 5 times 4 is 20. Okay, so I was just able, instead of drawing the table, you can just take the 2 separate, and we get the same probabilities here, 6 out of 20 for probability of red or blue with a number less than 4. Okay, so multiplying with the fractions is, makes it quite a bit quicker than drawing out your table every time. So fairly useful. Let's look at another example. Okay, so Jason here in the glasses, he rolls a standard 6-sided die. Rachel spins a spinner with 3 equal sections. What is the probability of rolling an even number and spinning a B? And then verify your answer using another method. Okay, let's start with drawing a tree diagram. We could spin an A, spin a B, or spin a C. If we spun an A, we could get a 1, a 2, a 3, a 4, a 5, or a 6. If we spun a B, we could get a 1, a 2, a 3, a 4, a 5, or a 6. So we go with squish, sorry. Or we can spin a C and get a 1, a 2, a 3, a 4, a 5, or a 6. And now we can sort of see all of these outcomes. So we're trying to find what's the probability of rolling an even number and spinning a B. So a B with an even number would be B2, B4, or B6. Okay, let's use a different one. So B6, B2, B4. So those are the 3 favorable outcomes, the ones where we roll an even number and we spin a B. With all the other ones, we spin an A or we spin a C, so not favorable. So we could say it would be 3 out of, well, how many total possible outcomes are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 3 out of 18 from our tree diagram. What else could we do? Well, if we wanted to find the probability of even number and comma B, we can just take the probability of even number and multiply it from its event, rolling the dice, and multiply it by the probability of getting a B, probability of getting an even number on a dice. Well, there's 2, 4, and 6, so 3 of the outcomes out of the 6 multiplied by probably getting a B is 1 out of 3. 3 out of 6 times 1 out of 3 is 3 out of 18. Okay, so we got the same answer both ways, but it's a little bit quicker to just multiply the fractions together, I would say. Okay. Okay, so just one last thing, just looking a little bit at experimental probability. So we did talk about this in grade 7. So we have theoretical probability, which is what we've been looking at so far with our tree diagrams and our multiplication of fractions. But just because you have a theoretical probability, doesn't mean that you're always going to get that. So for instance, if you flip a coin, there's a 50-50 chance that you'll get heads or tails. If you flip a coin 10 times, theoretical probability would tell us that you'd have 5 heads, 5 tails. But experience and experimental probability tells us that you won't necessarily always have exactly 5 and 5, because that's just not how randomness works. And so there's often experimental probability and there's theoretical probability, which can be slightly different. And I'll just quickly talk a bit about the end, how to make them closer together. So Gina is planning the time needed to get to her soccer game. There are 2 traffic lights between her house and the soccer field. These lights are red or yellow 60% of the time. So assuming you'd have to stop whether it was red or yellow. Gina wonders how likely it is that both lights will be red on her way to the game. So she modeled this situation by spinning a spinner divided into 5 equal regions twice. The table shows the results for 10 trials. So this spinner shows 3 out of 5 red, which is the same as 60%. 3 out of 5 is equal to 60%. Okay, so she showed on her spinner 60% red. And since she's going through 2 lights that are 60% of the time red, she was able to spin this spinner twice and see a simulation of what are the chances that when she's going to her game, she's going to get red lights both times. So for some reason, she was just really interested in this. So she did her experimental results. So in trial 1, she got red, red, and red. So both lights red, yes. Trial 2, she got green and green. Both times she got green. So not both lights were red. Another time she got red and green, green and red, red and red, red and green, red and red, green and green, green and red, green and green. Okay, so she's just doing this, spinning them 2 times for each trial, and then just seeing if they're both red. Okay, so A, what is the experimental probability that both lights are red? Well, in this case, with her 10 trials, out of the 10 trials, how many times are both of them red? Well, we have 1, what's that? 2, 3 instances. There's a 3 out of 10 experimental probability that both are red. Because in her experiment, when she tested this using her spinner, 3 out of the 10 times both lights were red. Okay? So what is the theoretical probability that both lights are red? Well, the probability of the first light being red, let's do this over here, you have a 3 out of 5 chance that the first light's red. You have to multiply that by a 3 out of 5 chance that the second light is red. 3 times 3 is 9. 5 times 5 is 25. And so you have a 9 out of 25% chance that it's theoretical, in the theoretical probability, 9 out of 25 chance that both lights are red. Okay, so let's compare the experimental probability with the theoretical probability. So in a sense, all it's asking is which one's greater? Well, it's 3 out of 10 or 9 out of 25 greater. We can do this a couple ways. You can either make them into fractions that have the same denominator, or we can make them into percentages. So 3 out of 10 is equal to 0.3 when you go 3 divided by 10, times by 100 is 30%. So So there's a 30% chance experimentally that it'll be red. 9 out of 25, if you go 9 divided by 25 in your calculator, you get 0.36 times by 100 equals 36% chance that the lights will be red. So the theoretical probability that the lights will be red is greater than the experimental probability. So how could Gina improve the accuracy of the experimental probability? Okay, we're assuming that the theoretical probability here is right and that the lights are actually red 60% of the time. The theoretical probability would be right. So how can she improve her experimental probability? There's really one answer: do more trials. Okay, so if you flip a coin twice, for example, you could get 2 heads when you flip a coin twice. That doesn't mean that there's a 100% chance that you get heads when you flip a coin. Now, you could flip a coin 3 times and get heads every time. But the more times you flip a coin, the more likely it is you're going to be getting some of each. You do 100 flips of a coin, and it should be a little bit closer to 50-50, but it could be maybe like, I don't know, 40 to 60. But if you flip the coin 1,000 times, I would guarantee that your number of results would be a lot closer to 50% and 50%. If you flipped it 1,000,000 times, I would guarantee that you'd be quite very close to 50-50. Okay, so the more trials you do in an experiment, the closer you'll be able to get to theoretical probability. Okay, just a couple little examples of how we can just use multiplication to find probability. So what's the probability that you roll 3 even numbers in a row with a 6-sided die? Okay, so this in the first roll, there's 3 even numbers out of the 6, multiplied by 3 even numbers out of the 6, multiplied by 3 even numbers out of the 6. So this is each of the rolls. There's 3 even numbers, so we can multiply them together. Now, I would say that it's always a good idea to simplify first if you're able to. So for instance, 3 out of 6 can be simplified to 1 out of 2 times by 1 out of 2. And you don't have to be able to simplify every fraction, but simplify as many of the fractions as you can, and that'll make it easier. So 1 times 1 times 1 is 1. 2 times 2 is 4 times 2 is 8. So you have a 1 out of 8 chance that if you roll a dice 3 times, you'll get 3 even numbers. Okay, and we can just use multiplication like that. It's really quite simple and quick. So what about this? What's the probability that when dealt 4 cards from a deck of 52, you will get 1 of each suit? This is a little bit more complicated. So what's the first, how many, well, part of this you need to know how many cards are there of each suit. Well, 52 divided by 4 is 13. So there's 13 cards of each suit. So if you wanted the first suit to be dealt to you, there'd be 13 cards of that suit out of the 52 cards in the deck. So you got the 1 card. Now the next suit, there's still going to be 13 cards of that suit because you haven't gotten that suit left. Okay, so let's say this was hearts. This is going to be clubs. Yeah, this is going to be spades. And this is going to be diamonds. Okay, so let's say there's 13 out of the 52 cards. You got one of those was a heart. You had a 13 out of 52 chance of getting a heart. Now that you've already been given a card, you have a 13 out of 51 chance of getting a club. Getting a spade, you have a 13, since you've been given 2 cards, you have a 13 out of 50 chance of being given a spade. And a diamond, you have a 13, you have all the diamonds still left in there. You've been given 1 of each of the other suits, but you only have 49 cards left in the deck. Okay, again, this question here is a little bit more complicated than really what we're needing to do, but I'm just showing that even this type of question, which is sort of complicated, we can figure out with just multiplying fractions. As long as we can look at for each situation here, so hearts, clubs, spades, diamonds, we can look at each situation and see what the probability is. And again, the order of these suits doesn't matter. But we can just multiply these fractions together and use our calculator. We can go 13 times 13 times 13 times 13, and I get 28,561. Okay, so there's 28,561 out of, so that's many possible combinations of getting 4 different suits in 4 cards, which is pretty crazy. But how many possible combinations of 4 cards are there? Could you be dealt in a deck? Well, since you'd be given 52 and 51 and 50 and 49, we multiply those together, 52 times 51 times 50 times 49, which gives you, so how many different combinations of just 4 cards in the deck are there? There is 6,497,400 different combinations, total combinations of 4 cards from a deck that you could be dealt. Okay, so anytime you're playing a game with cards and each person is dealt 4 cards, each one of you has 1 out of those 6,497,400,000 combinations. So what percentage is this? We can divide the top number by the bottom. 28,561 divided by 6,497,400 gives me 0.0043, 439. I times that by 100 to find my percentage, and I get 0.439% chance. Okay, so it's actually very unlikely that you'll get 4 cards, each from a different suit, when you were dealt 4 cards. There's only this much of a chance. So pretty neat to see. Probabilities and statistics this way is sort of cool. Okay. Mostly we'll be doing questions of this difficulty. Just thought I'd show you this because I think especially cards and possible combinations there are is interesting. Anyways, this is the last section of the year, grade 8s. Hopefully see you in September. Enjoy your summer. I will probably talk to you again on, or some of you again on Google Meet maybe. Otherwise, yeah, see you around.